Relative humidity. Relative humidity is a fairly familiar concept to most people, and it's a common parameter to work out, to calculate in meteorology as a measure of the degree of saturation of an air mass. So let's define relative humidity in percentage as the ratio of the amount of vapor in a given volume of air to the amount that volume would hold if the air were saturated. So we may write relative humidity as R, the mixing ratio, in grams per kilogram, divided by RS, the saturation mixing ratio, in grams per kilogram, multiplied by 100. And the convenience of using the mixing ratio is that the mixing ratio can be obtained from the dew point profile, the saturation mixing ratio from the temperature profile, and that's very easy to do on a skew-T log P aerological diagram, and even just visually you can see by the degree of closeness between the temperature and the dew point temperature profile whether or not the air is close to saturation. However, there are two ways of defining relative humidity. The American Met Society glossary defines relative humidity as the ratio of the vapor pressures, whereas the World Meteorological Organization defines, as we've just done, the relative humidity as the ratio of the mixing ratios. So, how similar are these definitions? Does it really matter which one we use? Well, again, a little bit of maths, so if you need to stop the video and work this out, fine. As we've seen earlier, the mixing ratios may be expressed in terms of this ratio of the specific gas constants, or the molecular weights between dry air and water vapor, and in terms of the relevant vapor pressure and the total pressure, P, in those two expressions there. So you can divide the second expression for R, epsilon E on P minus E, by the expression for the mixing ratio at saturation, epsilon ES all over P minus ES, as is done in the line below. Cancel the epsilons and invert the fractions in the numerator and the denominator to get the second expression. So what this has done is to show that the relative humidity in terms of the mixing ratios may be written as the relative humidity in terms of the vapor pressures, E on ES, multiplied by the extra term P minus ES over P minus E. If we then divide that equation by P, you end up with the next expression there, E on ES, 1 minus ES on P, all over 1 minus E on P. And we do that because, given the vapor pressure is typically much less than the total pressure, we can do a Taylor expansion on the denominator. So R on RS is approximately equal to E on ES by the numerator, 1 minus ES all over P, and then the Taylor expansion of the denominator, which is 1 plus E over P, plus expressions of order E on P all squared and higher. And we'll ignore those higher order terms. That then gives you a quadratic to expand as shown in the bottom line, and again when we get to it you'll ignore terms of E squared, for example, or E on P squared. So that's a little bit messy, but you end up with this term here, and we take the E on ES over to the right hand side. So the difference between the two definitions of relative humidity, R on RS minus E on ES, is approximately E on ES multiplied by 1 on P by E minus ES. Now this expression here, in the numerator we have the squared of vapor pressures, and on the denominator we have the sum of vapor pressures by pressure, and so that's of order, or of magnitude, the vapor pressure over the total pressure, which we've said is quite small, much less than 1, which means that the right hand side of the equation is approximately equal to 0, or R on RS is approximately equal to E on ES. In other words, it doesn't really matter which definition of relative humidity that we use, and because it's convenient we'll use the ratio of the mixing ratios. The departures occur when E large compared to P, and that's when the air is hot and dry, or when the pressure is small, that is in the upper atmosphere. But notwithstanding those caveats, we'll typically use R and RS to calculate the relative humidity. So how do we do this on a skew-T log P aerological diagram? Well, for this particular example, we have at a given pressure level, the temperature is 13 degrees Celsius, the dew point temperature is 10 degrees Celsius, and we can read off that the mixing ratios. So from the dew point profile, the temperature of 10 degrees Celsius, we go down the nearest isopleth. As it turns out, it's 8 grams per kilogram. And likewise for the temperature, a temperature of 13 degrees Celsius for that given pressure corresponds nicely to the 10 grams per kilogram isopleth. And so R and RS is 0.8, and multiplied by 100 gives you 80% relative humidity for that case.